In this video, we're going to do a few examples of solving problems using Lenz's law and Faraday's law. Our first problem involves a conducting loop of wire. So we have some type of wire that we have constructed into a square loop, and we are given the sides of the square, which are 0.02 meters. Now, throughout this region, we have an external magnetic field, which is increasing given this function, where t is time. So at t equals 0, there's actually no magnetic field. But as the time increases, as we move forward in time, the external magnetic field is moving in the negative z hat direction. Using our standard coordinate system, negative z hat is into the page. So we have an external magnetic field which is increasing into the page throughout this entire region. The loop has a total resistance of 10 ohms. So this wire is not a terribly good conductor, and so it has a resistance of 10 ohms. The goal of this problem is to find the induced current within the loop and the force that the left side of the loop feels as this magnetic field increases. Before we begin solving this problem, let's just review our relevant equations. First, we have Faraday's law, which relates the EMF, which we remember is an effective voltage. It acts like a voltage, though it doesn't follow all of the rules that voltage does, but it's good enough to use it in Ohm's law here. So we have the EMF, which is equal to negative n, where n is the number of turns in our loop. Here we're only going to have one turn in our loop, but we could have many, as in this copper wire here, where I have wound it many, many times. But in this case, we're only going to have one turn in our loop. And we have then the derivative of the magnetic flux with respect to time. Next, we have the definition of flux. This definition here works if our magnetic field is uniform, that is, it doesn't vary from spot to spot in space, which is going to be the case for all of the problems that we look at in this video. So then, in this case, the magnetic flux is simply equal to the magnetic field dotted with the area vector. And finally, we have Ohm's law, which will help us to determine the current once we know the EMF. And our general strategy for all of these problems is we're going to use Faraday's law really just to find the magnitude of the EMF, and then we're going to use our Lenz's law rules in order to find the direction. Before we begin solving this problem, let's just review our relevant equations. First, we have Faraday's law, which relates the EMF, which we remember is an effective voltage. It acts like a voltage, though it doesn't follow all of the rules that voltage does, but it's good enough to use it in Ohm's law here. So we have the EMF, which is equal to negative n, where n is the number of turns in our loop. Here we're only going to have one turn in our loop, but we could have many, as in this copper wire here, where I have wound it many, many times. But in this case, we're only going to have one turn in our loop. And we have then the derivative of the magnetic flux with respect to time. Next, we have the definition of flux. This definition here works if our magnetic field is uniform, that is, it doesn't vary from spot to spot in space, which is going to be the case for all of the problems that we look at in this video. So then, in this case, the magnetic flux is simply equal to the magnetic field dotted with the area vector. And finally, we have Ohm's law, which will help us to determine the current once we know the EMF. And our general strategy for all of these problems is we're going to use Faraday's law really just to find the magnitude of the EMF, and then we're going to use our Lenz's law rules in order to find the direction. So this minus sign in Faraday's law is really going to be accounted for by using the Lenz's law rules that we developed in the previous video. Okay, so now that we have established our equations, we can see our coordinate system is the standard positive x to the right, y is up, and z is out of the board. Now we're ready to start thinking about this specific problem. To begin with, we note that the magnetic field is 4 times t, where t is our time, into the board, because it is in the negative z hat direction. So I will place our external magnetic field here, and though I drew the magnetic field vector down here, it is uniform everywhere throughout the page, and it is increasing into the board. How do I know? Because as t goes up, the magnetic field, the magnitude of the magnetic field gets bigger and it points into the page. So I'm getting a stronger and stronger magnetic field, more magnetic flux, and that field is pointing into the page. Okay, now what we can do is we can write down an explicit equation for our magnetic flux. That is, we write down our magnetic field, our external magnetic field, and we dot it with our area vector. Now, our area vector looks like L squared, and we have to pick a direction for this area vector. Remember that the area vector is always going to be perpendicular to the area enclosed by the loop. So this area is in the plane of the board, which means that our options for picking an area vector are either out of the board or into the board. Those are the only two vectors that are, or directions that are perpendicular to the board itself. Because the magnetic field points into the board, we will choose the area vector to point into the board also, giving us a total flux when we take this dot product of 4L squared times t. Now, this flux clearly explicitly depends on time, and we can take its derivative. That is, the derivative of the flux with respect to time is just 4L squared. Now that we have our derivative of the flux, we can use our induced current equation, or we can use Ohm's law to find the induced current, where the induced current looks like the magnitude of our EMF divided by R. Now, the magnitude of our EMF is equal to N, which we've said is 1 in this problem, multiplied by the derivative of our flux with respect to time. So we can simply substitute in the derivative of flux with respect to time, d phi dt, into our induced current equation here, or into Ohm's law, which is what we're using. Okay, finally we plug in values for L and R, and we get our current as 16 times 10 to the negative 5th amps. So there should be a minus sign there. And that comes from simply plugging in values explicitly for L as 0.2 meters and the resistance as 10 ohms. Now, the next thing that we need to do, now that we know the induced current magnitude, is we need to use Lenz's law to find that direction. So our Lenz's law rules state first that we find the direction of the magnetic field through the loop. Well, that is into the page. The external magnetic field through the loop points into the page. Our second step in Lenz's law says that we figure out whether the flux is increasing or decreasing in that direction. Well, the flux magnitude is clearly increasing into the page. I'm getting more and more magnetic field into the page, so my flux is increasing in that direction. Next, what we can do is that we can figure out that if the flux is increasing in that direction, the magnetic field that is induced by the loop will oppose that external magnetic field, which means that our induced magnetic field should be out of the page. We are opposing the increasing magnetic flux into the page. Finally, we use our right-hand rule to say that if the induced field points out of the page our induced current, which is generating the induced field. Remember that the induced current generates an induced magnetic field. Here I realize that this is not exactly a circular loop, like when we learned our right-hand rule for a loop, but the concept still applies even if the loop is square, for example. So our induced current therefore points in the counterclockwise direction. Now, our final task is to find the force on the left-hand side of the loop. To do that, what we're going to do is we're going to take the induced current and we are going to find out the force due to the external magnetic field on this current. Okay, well, I know that my induced current on the left side of the loop is going to be pointing down, and I know that it has this value here. I know that my L vector on the left-hand side of the loop here will be pointing down, so in the negative y hat direction, and it will have a length of 0.2 meters. So I can write this in. So my I induced is 16 times 10 to the negative 5th amps. My L vector is going to be negative 0.02 meters in the y hat direction. And now I'm going to cross that L vector with my external magnetic field, which is negative 4 T Z hat. Plugging in values for this, we find that the force vector is 1.28 times 10 to the negative 5th. Multiplied by T, our force still depends on time because the external magnetic field is getting stronger and stronger, which means that our force is getting stronger and stronger on the induced current. And it points in the positive x hat direction. You can find this either by taking the cross product of these two vectors, or you can use your right-hand rule where the index finger points in the direction of the current. My other fingers are going to point in the direction of the external magnetic field because we're interested in the force due to the external magnetic field, and our force points to the right in this case, in the positive x hat direction. Notice that even though the force is increasing with time, my current is not, because the current depends on the rate of change of the magnetic field, or the rate of change of the flux, which depends on the magnetic field. And that is a constant. The magnetic field is increasing into the board at a constant rate, and therefore my induced current is constant. The force depends on time because the force takes into account the induced current as well as the external magnetic field, and that external magnetic field is continuously increasing with time.